This question says make it a little bigger for you. A grocery store manager did a study to look at the relationship between the amount of time in minutes customers spend in the store and the amount of money in dollars they spend. Results of the survey are shown below. Here's the results. So in other words, does when people spend more time in the store, do they tend to spend more money? Like like this person spent, so this is the first person here. This person spent 10 minutes in the store and only spent $1, bought a gumball or something. The second person spent 26 minutes in the store, right? And spent $250. The third person spent 18 minutes in the store and spent $150, et cetera, et cetera, et cetera. So the question is, does how long they spend in the store, is that connected? Is that related to how much money they spend? Now, do people really care about things like this in the real world? Yeah. Businesses care a lot. Basically, they're wondering if more time in the store makes you spend more money or encourages you, is connected to you spending more money, then they're going to have an interest in you spending more time in their store. And so they're going to spend money on making their store nice. They're going to hire a lot of employees who can keep everything clean and decorated nicely and pay for nice air conditioning and do whatever it takes to make the inside of the store nice, if that ends up encouraging you to stay longer and results in you spending more money. But if there's really not a big connection, if people spending more time in the store, they're just loitering and hanging around and not really spending more money, then they're not going to care as much to make the inside of their store so nice. So that's the deal. Yeah, businesses care a lot about this. How do we examine this kind of relationship? Well, the first thing they ask us to do is find the correlation coefficient R. There's the answer. How do we get that? Well, let's go to the notes. And here we are. We're on the Unit 4 notes. And this is testing linear correlation. We know that because, right away they asked us to find the correlation coefficient, right? So we're testing linear correlation, number 10 down here. Go to the online calculator, regression analysis. Copy and paste data into X and Y. Click plot the points. All right, let's do it. We'll go there. So regression analysis. Let me go there. It's the second to last. It's regression analysis number 24. There it is. Second to last calculator function, number 24. Regression analysis, it opens up and we've got this little window. So notice the X down here and the Y down there. The X and the Y is where we're going to copy and paste the table values. So I'll go back to the problem. Here we go. And I'm going to copy the X values. Here we go. Copy those. Copy those X values and go on back and paste them in. But, you got to put commas between them like always. Don't need to fix the spacing. Just put your commas in there. All right. And now we got to put in the Y values. So now go back to the problem, grab the Y values. There we go. There's the Y values. Copy those. Back to the calculator. Paste in the Y values and put some commas between them. So we put in the X values, put in the Y values, put the commas between them. And hit the calculator or hit the plot points, right? It said hit plot points. I'm going to plot the points and see, it makes that nice graph there. That graph is a scatter plot. It's showing you, so those are the 8 different dots. And it's showing you that they really fit a line pretty well. And it puts a line right through the middle of them. So yeah, so that's the scatter plot. So here, let me bring that over where I can draw on it for you and show you exactly what I'm talking about. There we go. So yeah, so this is 1, 2, 3, 4, these dots, 5, 6, 7, 8 little dots. So those dots are these 8 points, like this one, over 10 up 1. Where's that? Right here. Over 26 up 250. Over 26 up 250. It's probably that one. Over 18 up, etc. These are, remember, these are X, Y, 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 X, Y points. That's how they started off, in the original question right here. Right there. There. X, Y, time and money. This is customer number 1, customer number 2, customer number 3, and how much time and money they spent in the store. Time and money. So it's showing us, is there a connection down here? This is time on the x-axis. This is the y-axis, which is money, dollars, right? So, so so this dot right here, this looks like it's over like 17 or 18 and up about about $150. The person spent about 17 minutes in the store. That's, or maybe it's 18. I'm just looking at the chart. So this person, it's this third. Here's the first customer. Here's the second customer. It's that third customer who spent 18 minutes in the store and $150. $150. This is dollars. Again, this is time. Right? A third customer. So this dot is customer number 3, for example, right here, who spent about $150 and 18 minutes in the store. You may say, well, it doesn't hit 18 seconds. Well, close enough. So there's this, that's a scatter plot. That's the dots. Those are the 8 customers. And then the computer automatically calculated the line that fits through the middle best. This line is called the best fit or regression line. It's the best fit or regression line. It's also called least squares. That's another name. It has a lot of names. We'll usually call it the best fit line or the regression line. It's the line that fits best through the middle of the dot. So the calculator did all that for us. Let's get back on track with the questions. What is R? Well, we see the answer right here. Where did we get that? Somewhere. Let me go grab it for you. Yeah, it's right down there, isn't it? In fact, I probably could have just copied that whole page, huh? Let me do that. Let's copy that whole page. Bring it on back. Should have just done that the first time. And paste it in here for us. There it is, the whole page. Okay. Yeah, so R, whoop, my pen going. R is right there, 0.85. It's one to round to 2 places. And so you get that. And then next, they want HO and H1 and find a p-value. Well, how do we do that? Well, HO and H1, if we go up here to the notes, it tells us that HO is that weird looking P, which is actually called rho. I'm not going to quiz you on the name. It's a Greek R, even though it's a P. Well, it's a weird P. It's a Greek R, really, called rho. Anyway, just think R. R is 0, and H1 is R not equal to 0. And remember if R is 1, well, here, let's do it this way. If R is 0, that's when the dots either see, you can see the example here. If R is 0, the dots are just crazy. They're just not making a line at all. If R is really close to 0, you say, what about this one? Well, this one's also, this is a curve. It's not a line. So R equals 0, it means not linear. Remember that? Remember when your R, your correlation coefficient, R is a measure of how much the dots make a line. And so when R is 0 or really close to it, that means the dots don't make a line. Not linear. Whereas when R is 1, or really, like right here, R is 1 or really close to 1, like 0.86, the dots form a pretty tight line, pretty good line. That's why we say down here, the HO is R equals 0, meaning not linear, and the H1 is R is not 0, meaning it's far away from 0, so the graph is linear. So we're testing to see, are those dots forming a pretty good line, or are they not? Are those dots forming a pretty good line, or are they not? So we do a hypothesis test. HO is going to be no. The dots the R is close to zero. They're not linear at all. They're not making a line. And H1's saying, they're not equal to zero at all. They're far from zero. They're making a nice line. So that's what we're testing. So we come back to the hypothesis test here, and we're going to put in R equals zero versus R not equal to zero. And then we're going to go to the calculator and get the p-value. What calculator? Same place. Oh, we already done it, huh? P-value is right here. Here's the p-value, 00729, so 0073. And so that's how we get that. Oh, yeah, just 3 places. So 007, there's our p-value. Okay. And so now what does that mean? It starts going right into the statistically significant or insignificant evidence. Is there? Well, they're skipping a step. I'll do it just to remind you. We've done it so much, you probably know. We need to compare the p-value to the alpha level. They kind of skipped it. They're assuming we know it and can do it. So let's do it. What's the p-value? Well, we just said the p-value is 0.007. What's the alpha level? Right there, 0.05. 0.05. Okay, so which of those is bigger? If you're not sure, line up the decimal, right? Decimal right over decimal, 0.007, and then just fill in the blanks with zero. So it's 50 compared to 7. 50 is bigger. It's that way, right? This guy's bigger. He's on the wide side of the symbol. He's bigger. Again, line up the decimals and fill in blanks with 0, 50 compared to 7. So 50 is bigger than 7. Fill it in here if it helps you see it. 50 is bigger than 7. So, all right. So what does that mean? Well, you know the saying, right? If the P is low, then the HO, which is the null, must go, meaning go away. So if the P is low, the null must go. If the P is low, is our P value low? Yeah. Our P value is less. Our P value is indeed low. So if the P is low, the null must go away, which means reject the null, right? Reject the null, keep H1. So we come up here. This is the one we're keeping. Oh, by the way, and remember, HO is always, every time, oops, keeps doing that. Okay, HO is always weak evidence, and H1 is always strong evidence. Every time, every hypothesis test, you've done a lot of those now. HO is weak evidence, H1 is strong evidence. So what are we doing? We are keeping H1. So we're going to say, okay, keep H1, come right on back and keep H1. Believe H1. What does H1 say? It says R does not equal 0. So R does not equal 0. Strong evidence. And remember what R not equal to 0 means again? Come back. If you're not sure, go back to the notes. Here it is. R not equal to 0 means linear. If R is equal to 0, that means not linear. But if R is equal to 0 or not equal to 0, that means it's, R is not very close to 0. So R is more like this or this. So the dots form a line. They're pretty tight in a line. It's linear. R not equal to 0 means linear. Come back and go, oh, okay. So R not equal to 0 means linear. There's evidence that the dots are pretty linear. They're forming a pretty good line. And we saw that, just by looking at the picture. These dots aren't perfect, but they kind of do go in a line. Some of these are a little messed up, but generally the dots kind of go in a pretty good line. So yeah, we're not surprised that the hypothesis test results told us there's strong evidence that the dots go in a line. R is far from 0, is not 0 at all. In fact, R is 0.85, right? That was our value for R right there, 0.85. It's not close to 0 at all. It's closer to 1, which means the dots are pretty tight as a line. All right, so which one of these results is that? Well, remember, strong evidence is the same as significant. Strong means significant. Like if something's significant, it's weighty, it's heavy, it makes a big difference. So that's what we're looking for. So significant, yeah. Insignificant, no. Insignificant, no. Yeah, so it's one of those two significant ones. Which one? And thus, the regression line is useful or the regression line is not valid. Oh, which one? Well, let's go up here. and the notes will guide us. Let me show you everything we need. So really, I should have done this earlier probably. It's either going to be this box or it's going to be this box, depending on which way the p-value went. Which way did our p-value go, right? Because this p-value less is p-value greater. What was ours again? Back here, it was p-value less than alpha, less. So we come back here and we go, oh, it's this one. P-value less. What does it say? Then there is strong evidence that the two variables, x and y, have a linear relationship. On a graph, the dots generally fit a line. Yeah, we saw that. So we can use the linear regression equation. So we can use the linear regression equation. It's useful. Come on back. So thus, the regression line is not valid? No. It's this one. Right? This is the one, right? It's significant evidence, strong, significant evidence. The regression line is useful. There's our answer. Okay, let's keep going. A lot of questions here. Next comes R squared. What's R squared? It's on our outputs right here. No, that's not it. It's right here. R squared is 0.725, so round that wherever they want, 73. And what does that mean? What does that mean? Well, it says it right up here in the notes again, somewhere. I believe it does. Let me see if I can find that for you. There it is. R squared is the percent of variation in the y variable that is connected to variation in the x variable. Yeah, that's tricky. So, when two things are connected, they're not the only things that are connected. So, for example, I might do a graph. Well, let me just stick with this graph. We are graphing on this problem. We are graphing time in the store versus money they spend, right? And the more time they spend, the more money they spend. But yeah, that's not the only thing. Time, does time, is time connected to money? Yeah, for sure. But it's not the only thing connected to money, right? If this is Christmas season, people are probably going to spend more because they're buying all their Christmas presents. If this is not Christmas season, they might not be spending as much money. Or if it's Black Friday, people spend money anyway. So the point is, time in the store does affect money. Yes, they are connected, but they're not the only things. Money is also affected by what the season is, by how the economy's going, right? By how the competition is doing. Other things affect it, not just time in the store. Time in the store isn't the only thing that affects how much money people spend, right? Life is complex. Things are complex. Many things affect many different things. So the question we're asking is, all right, so R squared is the percent of change in Y that is connected to variation or change in X. How much does X affect Y? What percentage of changes in Y are due to changes in X? Well, in our case, that came out to be 73%. So that means 73. So our answer then is this one right here. 73% of the variation, the change in the amount of money customers spend is connected to the amount of time. That's a really important thing for a store owner to know. 73% of what they spend in the store is going to be connected to how long they're in the store. Other things will affect it as well, with the other whatever's left over, 27%, but 73% of how much they spend in the store is connected to how long they spend in the store. So that's an important number, R squared. All right, let's keep going. Next, we need to find the equation of the linear regression line. So it's right here. It's in the output somewhere. There it is, right there, the regression equation. So I just copied it down from right there. Just tap it on in there. Yeah, I want you to round to two places. Okay. Now, part G. Oh, and that's the equation of that line. You know what I mean? By this blue line. That's his line equation. That's this. This right here, remember, is the regression line. This is the regression line. This line right here. And there's his equation, regression equation. That's the equation of that line. Kind of like y equals mx plus b. Remember that from earlier days, like slope and all that. That's what this is. I'm not going to write all that out, but that's what this is. Okay. So then we're going to use that. That's an equation, a relationship between x and y. So use the model to predict the amount of money spent by a customer who spends 20 minutes at the store. So in other words, this is a relationship. It's a connection, write it over here, between X and Y, negative 70.77 plus 11.33x. This is connection. Remember, what is X again? They told us up in the beginning of the problem. Well, X is always the first and Y is the second. So X is time, Y is money. So X is time, Y is money. So this is time in the store in minutes, and this is money they spend while in the store. Let me write it over here. So X is time, Y is money. Okay. So this equation is the equation of the line and thus the relationship between X and Y. Where'd we get that from? The computer gave us that. That's the when it graphed this line. We just gave it the data and said, plot it, calculator, and it put these 8 dots on the graph, and then it automatically calculated the line that fits best through the middle of those dots. That line is how those dots relate to each other. That's called the regression line. The best fit regression line. Like that too. It's the best fit. It's the best fits right through the middle. The best fit regression line. And then the equation of it is right down there. That's the equation of that line. So that shows how those dots relate, how the X values and the Y values relate, connect to each other. So then we can use that now to predict things. Specifically, if a customer spends 20 minutes in the store, what are we going to do? Well, we're going to plug in 20 for time. So we're going to take our calculator. We're going to go, we're going to go Y equals negative 70.77 plus 11.33 times 20, right? Because this X right here is 20. They're saying time is 20. X is time. They're saying a customer spends 20 minutes in the store. How much money are they going to spend? So I just need to calculate that on my calculator. So negative 70.77 plus 11.33 times 20. Let me go to the scientific calculator, and I'll do that. Come on down here. So what was it again? It was negative 70.77. So negative 70.77 plus 11.33 times 20 equals. I got 155.83. See that? 155.83. That means that's how much money the person's going to spend who spends 20 minutes in the store on average. That seems to be the relationship between time in the store and money spent. The calculator gave us that line equation. We used it. It's from the dots. So let's go back so we can say, okay, so it came out to be, Y came out to be 155.83. That's money. And they said to round to this whole number. So that's $156, right? Give you $155.83. That rounds to $156, which is the answer. So a customer would spend about $156 if they spent 20 minutes in the store. That's how much you can expect them to spend in your store if they spend 20 minutes in the store. All right. So we use the equation. Oh, by the way, notice it said there, if you answered on part C, the use of regression line is not valid. We did it. So we didn't have to bother with that. Let's go on. H, interpret the slope of the regression line in the context of the question. The slope. Let me write the equation again down here. Y equals negative 70.77 plus 11.33x. So which of those numbers do you know is the slope? Well, the slope is always right here. It's the number next to it, which it'll tell us in the notes up here, if you want to look in the notes. And it doesn't. maybe it doesn't totally tell us that. All right. Well, it doesn't say a lot there, but anyway. So slope is the number next to X. So slope is always the number next to x. That's the slope. And then 11.33. And then the notes do say, what the notes do say, I'm gonna go back up here to the notes again. The slope is, oh yeah, yeah, that's right. See, it's right there. It's that number next to x. There it is. Slope is b. They're calling it b, a and b. It's that number next to x, and then you put it over 1, and it means when x goes up by 1, y goes up by b. Okay, so let's do that. Let's put it over 1 when and slope is, I don't know if you remember, it's rise over run. It's y over x. So it says I keep going back and forth. So I'll go back here one more time. See, change in y over change in x. That's what slope equals. Change in y over change in x. Okay. Back to it. So change in y over change in x. Okay, what is y in this problem? What is y? Y is money and x is time. So that means it's time on the bottom and money on the top. And notice they're both positive. So that means plus 1 more minute results in $11.33 more spent by the customer. You see how I'm coming up with that? That's what that slope is telling us. Again, the slope is the number next to x. You put, why did we put it over 1? Because we wanted to make it look like a fraction. That doesn't change the value. I couldn't put it over 2, for example, because that'd be a different number, right? 1133 divided by 2 is not 1133 anymore. But if you just put it over 1, dividing by 1 doesn't change anything. And that way it looks like a slope. It's a lot of what we do in math and science is make something look different. I call it plastic surgery. You remove the wrinkles, make it look different so you can answer the question you're trying to answer. We made it look like a fraction. We didn't change the value. It just looks different. It's the same person. So I say that weird plastic surgery statement just to help you remember we're changing the way it looks. We're removing the wrinkles, but it's the same person. So it's the same value it was before. Putting it over 1 doesn't change the value, but it makes it look different and makes it look like a slope. Why do we need it to look like a slope? Because we're told slope is change in y over change in x, so we need 2 numbers. So that means the number on the top is y, and what is y in this problem? Remember, y is money. Where did I get that from? Well, it's because back in the original table, the first is always x, the second is always y. So y is money, x is time. It's always x first, then y. So back to it. So this is, I'm getting totally lost in the problem. There we go. So this is money over time, and they're both positive. So 1 more minute spent in the store, time-wise, is $11.30 more spent in the store. That's what that slope is meaning. So there it is. For every additional minute customers spend in the store, they tend to spend, on average, $11.33 more. Final question. A lot of questions here. Halfway through the alphabet here, A, B, C, D, E, F, G, H, I. Interpret the y-intercept in the context of the question. What is the y-intercept? Well, that's the other number. This one right here is the y-intercept. It's the number not next to x. Again, the notes will tell you. Let me go back to the notes. Here they are. The y-intercept is a. See, that's the first number, the number not next to x. And what does the y-intercept mean? It means when x equals 0, y will equal that value a. Okay. Again, when x is 0, y is a. So when x is 0, y is a. So when x equals 0, y equals a. And what is a? Y equals negative 70.77. The y-intercept. That's what it means. Now, what does that mean in the real world? You got to keep remembering, you can't forget, what is x, what is y? Y is money. So this is money, negative 70.77. And x, remember, x is time, 0 time. So that means if somebody spends 0 time in the store, they're going to spend negative $70.77. That's ridiculous. How do you spend negative money? That's ridiculous. So the point is the y-intercept has no practical meaning for this study. You see why that is? Because you can't, if you spend no time in the store, unless it's an online store, so we mean no time period, online, in the store, anywhere, you're not going to spend any money. It's not negative $70.77. That's crazy. So that's crazy. Toss that out. No practical meaning. But sometimes it could. It could have had meaning. In some situations, it will. If you're measuring different things, you just got to be real. I can't give you one size fits all. You just got to be real. What I mean real, you got to remember what X is, and you got to remember what Y is. X is time, Y is money in this problem. So no time, you're not going to be spending money. No time in the store, you're not going to be spending any money in the store. That's crazy. But other situations, it could be. It could be. Could have a practical meaning. You just got to make it real and think if it's real. Think if it's practical. So there we go. A lot of different questions.